Good day everybody, my name is Andrew Copeland. I'm the Technical Director at Knight Piesold Consulting in Johannesburg, and I'm going to take you through a presentation on filtered tailings disposal. Now, filtered tailings disposal is certainly something that many mines are having to start considering these days because of the number of failures that have taken place around the world, and filtered tailings is seen as one of the options to make sure that water is removed and more stable facilities are created. So I'm going to take you into this presentation and look at what are the drivers, in addition to stability, that we need to consider when looking at dry stack tailings facilities. What are the system components that make up these facilities, and run you through a couple of examples and one case study. So if we look at the drivers for filtered tailings, stability, no doubt, is the number one. If you can remove water from your tailings, you take away the biggest driver for liquefaction, biggest driver for any sort of failure to take place. And in addition to that, if you can compact the tailings, you get a much denser facility and there's less chance of failure taking place. In addition to that, if you're able to remove water from your tailings, you're able to lower water consumption. And particularly on large mines, in arid areas, in desert areas, that is a big driver. And the cost of bringing in water, whether it's desalinated water or just bringing it in from another area where there's competition for water, water scarcity, that's a big driver, and that cost can be significant. In addition to that, if you've got very little water in your stack, in your facility, then there's much lower risk of contaminating surface and groundwater. And in particular, if your tailings has the potential to generate acid, the acid mine drainage potential becomes much lower. Seepage is much less, and depending on the type of tailings, depending on the area, you may or may not even need a lining system, which is quite common in certain areas and certain jurisdictions like South Africa, where that's becoming a requirement. It may also be possible to reduce dust generation by wind from your facility, and it may also be possible to do progressive rehabilitation on a much earlier basis and not leave it right to the end of the mine life. So it lowers the closure costs. So these are really good drivers for filtered tailings. This is a sort of generic slide that tries to indicate the progression from a slurry through to a paste, through to a filtered or cake type material in terms of thickening and dewatering of slurries, of tailings slurries. And the red numbers at the top indicate the types of water consumption that you can expect if you're in the slurry range, the types of water consumption in the paste and in the cake range. And so if you're able to filter your material down to a cake, you're probably using three times less water than you would be if you were doing conventional slurry disposal. However, there's a whole lot of things that are required to remove that water, and if you're into the cake zone, you're having to use filter type technology to do that. And once you start filtering your material, then you've got to start look at how do you convey it, or how do you truck it to the disposal site, as opposed to using pumping systems, whether it's centrifugal pumps or whether it is positive displacement pumps. So these are the sort of things that you have to consider, and the properties of the tailings that change when you dewater it. There are a range of dewatering and thickening processes that can be used, right from the top line of conventional type thickeners with low solids concentrations, right down to your belt filter or filter press type activities. And in the right hand columns here, I've tried to give a little bit of an indication of what are the relative capital costs and what are the relative operating costs for these different systems. And many mines are still trying to dispose of their tailings using high rate thickening. It's the most cost effective of all of them if you look at capital and if you look at operating costs. And as soon as you start looking at filtered tailings, Your capital cost may be of the order of 5 times greater, and your operating costs may also be of the order of 5 times greater than the other systems. And so moving to a filtered dry tailings is not an easy equation in terms of the filtered cost for the equipment and operating it, despite all the drivers related to water. If we look then at the transport systems, the conventional transport system for slurries is centrifugal pumps, and for conventional thickened material or even high density material, centrifugal pumps work well. And as long as your yield stress is not too high, you're able to continue using centrifugal pumps, and that's the cheapest form of transporting a tailings slurry. As soon as you get into the paste regime and you start having to look at positive displacement pumps and the yield stresses go up, you start to get into much more expensive pumping systems. You need, you've got higher pressures, and then you need thicker walled pipelines. But then if you get into the dry stack situation where you're transporting a cake, you can start to consider conveyor systems or even trucking. And depending on your distances and depending on your tonnages, depends on the type of system that you might consider. And conveying is typically a very efficient form of transport, but it's not as cheap as normal slurry pumping. This next slide is a simplified illustration of the differences between disposing of a cake versus disposing of a paste. So I'm going to concentrate mainly on the bottom slide, which is looking at a more of a dry stack type system where you've got a conveyor bringing material to the crest of a facility, and it dumps it over the edge. Now, you may build it up in very thin layers, in horizontal layers. You may allow it to be deposited from a particular height, and it slumps down on its own. And so there are various different ways in which this can be configured, but ultimately you may still need some kind of containment walls to form this, and initially you need some form of elevation in order to deposit this, unless you're just building it up in consecutive layers, which may also include compaction. This next slide gives you a little bit of an illustration of, as you move along the slurry density scale here up to the filtered region, say a density of 1.8, your water consumption is dropping, and your thickener and pump operating costs and your transport costs start to go up. There's typically an optimum region, and that's what I was talking about, is many mines are happy to operate in this optimum region, and to move into the filtered region takes you into a different regime in terms of costs based on this type of equation. So then if we look at a filtered tailings circuit, a typical setup in a plant, you've got to have a dewatering component that starts with a thickener, and that thickener underflow then feeds to the filter equipment itself. And obviously there's a range of filtration equipment, and I'm not going to talk around all the different types. I'll leave that to Multotec to explain, but you've obviously got disc filters, you've got belt filters, and then you've got different types of filter presses. And all those different pieces of equipment result in a cake of different levels of moisture, where typically your belt filters and disc filters result in a slightly wet cake, as opposed to your filter press, which can bring it right down to something that's very dry. And the drier it is, the more energy you typically need. Then in terms of transporting it, as I've mentioned, there's a range of systems you can use, but a conveyor system with some kind of stacker and spreader system is common. But if you do have a conveyor system, you often need bypasses for downtimes. You need stockpile areas to make sure that when you are either moving your spreader forward and advancing it, you've got somewhere to dump the material. So you either need a bypass at the tailings facility itself, or you need a bypass at the plant when there's upset or maintenance conditions. And if you're going for some sort of trucking system, You can consider a silo where the tailings is deposited into a silo and then it's batch deposited into a truck and transported to the facility. On the tailings facility itself, you may still need stormwater management systems. Whatever stormwater lands on that facility may result in runoff, and that is quite probably contaminated and needs to be kept separate from any surface water system. So that needs to be included as part of the design. So some of the pros and cons for filtered tailings facilities. First of all, can the tailings be dewatered? How easy is it? What is the rheology of the material? What is the grading? And obviously tailings that have a high clay content are going to be more difficult to dewater, and you need more equipment if you do have to dewater it. And the finer the material is, the more often the filter cloths are going to be clogged up, and you need to have either flushing systems or you need to start replacing those filter cloths on a regular basis. So there are those types of operating situations that you need to keep in mind. And then there's upset conditions. What do you do if your filtration system is not working? Where does that tailings go? Because it can't now be conveyed and trucked if it's in a slurry form. So these are factors that need to be built into the designs. And again, you need to understand what the production rates are. There's some mines that would love to be able to dewater their tailings down to some sort of cake, but they're producing 100 or 200,000 tons a day. That needs a lot of equipment, really high costs. And the technology maybe hasn't reached the point yet where those costs are coming down and that size of equipment is being produced without it taking up rugby fields of equipment. So those are some of the things that are facing us in terms of converting from hydraulic disposal to dry disposal. And then, can the cake be easily transported? What are the properties of the tailings? Does it stick to the conveyor belt? Does it hang up in the transfer points and in the chutes? And what sort of spillage do you need to cater for? What sort of belt cleaning and scrapers do you need? Continuing in terms of pros and cons of these systems, how easy is it to stack the tailings? What sort of starter works do you need? Do you need an elevated situation where your spreader can start off and you've got space where it can deposit? Or can you start off right at ground level and build up from ground level in layers? That depends on whether you're using a spreader, whether you're using trucks, and whether you can let the material flow. If you're able to build up a starter wall and let the material flow, that's beneficial because then the material, your equipment stands in one place while the material flows away. Also need to consider whether you build a radial stacker type system or whether you build something that's a face advancing stacker type system. Also, as I've mentioned before, do you want to compact the material for stability? But then what happens in the rainy season? You can't get out and compact the material, it's too wet. So what do you do? Do you continue depositing or do you stockpile it and wait for the dry season? And I've seen that done, and we'll come to an example of that. And then for your stacker systems, you need these bypass nodes, you need stockpiles for the downtimes. And then if you've got very big equipment, what about the bearing capacity of the tailings in terms of advancing the equipment over the tailings as you go? Now, if you're advancing very fast, the material may not have built up enough bearing capacity in a short space of time. So again, do you need to compact to enable the bearing capacity to be sufficient such that your equipment doesn't settle or tilt such that it starts to become unstable, particularly in a high wind situation. And then there's the advantages or disadvantages of being able to rehabilitate the facility sooner rather than later. And if you're building it up in layers, then definitely you can rehabilitate the side slopes. If you're building it as an advancing face, you can rehabilitate from behind it. I'm going to talk about a couple of examples now just to illustrate what is being done in certain parts of the world. Here is a filter plant. It's in the process of being built and commissioned at this time when I took the photographs. And you can see two sets of filter presses located near the top of the building, depositing the filter cake down onto conveyors midway, and those conveyors deposit onto this outlet conveyor that puts the material onto a stockpile. And so that's the arrangement that they've got there, in addition to the upfront pre-thickening thickener that sits off to the side of the plant. Now what we need to remember is that this is a batch process. In this particular case, because it's a filter press, it has to dewater and then it releases the material, and so you don't get a continuous supply of material, and hence stockpiling the material and then in this particular case loading it into trucks would work well. The next operation here, looking at the upper photograph, you'll see on the right hand side two sets of filter presses. These two filter presses drop the material down onto a conveyor system that deposits the material inside an undercover storage area. Now this is because it's in quite a high rainfall area, and it's also in a seismically active area, so they need to keep the tailings at a specific moisture content to make sure that when it's trucked out to the facility it can be compacted, and if that moisture content is too high they cannot compact it. And it also means that if it's raining they can't deposit, and so they have to have this shed to store the material. And for this particular process plant, again, there was a pre-thickening area, and part of the pre-thickening was using cyclones. The cyclones helped dewater some of the tailings before it even goes into the thickener, and that obviously reduces the time that you need to then spend using the filter presses if the material is already partially dewatered. This is the filter stack for that particular facility, and you will see that it's in a very mountainous terrain, and this material is built up as quite a steep-sided facility, but because it's compacted, those slopes are safe in terms of stability. They also keep the plastic on the sidewalls here to try and reduce infiltration into the facility, again to control stability. Just a slide illustrating for another mine in a very arid area where belt filters were used for a copper tailings. These belts, you can see two are operating and the one is down, and that's one of the things that you need to understand, is that sometimes you have to take these pieces of equipment out to replace the filter cloth and things like that, and so there are times when you won't have the full capacity of, say, all three belt filters, as in this case. Those three belt filters then feed onto a common conveyor at the end, and that common conveyor then takes it out to the facility, which is shown on the next slide. So this is the spreader system at the end of the line. It's a radial type stacker rotating off the tripper system, and it's got a crawler system that allows it to rotate. And in this particular case, the tailings is coming out at a 20% moisture content, and it's able to create a dump with an 8-degree side slope. And this is what it looks like looking at Google Earth pictures. Your plant is sitting over here with the belt filters and the pre-thickeners off to the one side, conveyed overland. This triangular area here was the first radial stack, and then they started using the second radial stack and depositing the material up against a boundary wall on this side over here. This is a picture of the same facility a number of years later, and you can see that from the black line to the red line they've pivoted that facility, and now they're depositing in this area over here and filling up this zone. I'm going to show you one particular case study which is not too dissimilar from the last example. Here we have a situation where you have a plant site over here with a number of belt filters located here, and from there the overland conveyor runs out to the tailings facility, which is quite some distance, about 3 kilometers from the plant site itself. And they have a stockpile or bypass area in the plant, so if there's upset conditions there, and they also have a bypass node out on the tailings facility itself. This is a close-up view of what that facility looked like at the design stage, and I'll explain to you how things changed during operations. But essentially it started off with the tailings coming in from the overland conveyor to the main transfer point. This stacker system was built up against a side hill. There's a mountain on this side over here, and it meant that it was 40 meters above the local terrain. And that meant that they had an advantage of being able to stack from an elevated position and let the tailings flow. They didn't need to compact it for any stability reasons. There was open land, and so they were able to let it basically flow out at its angle of repose. And the idea was that this would be a pivot system, so the first pivot would rotate round in this direction in phase 1, and while that phase 1 was being built, a main wall would be generated or constructed in this direction using waste rock, which would allow the next set of conveyors to be built, and then the whole stacker system would be moved forward to this position over here where it's written main wall. And from there the second pivot would take place, and after that area has been filled, there would be a third pivot for this phase 3 area, and the boundary walls would be built with waste rock to keep it within that particular zone. So that was the concept at design, and it comprised a series of belt filters. Initially there were 4 belt filters, but they found they had to increase that to 6 in time because of upset conditions and because of the rate of dewatering. Each of those belt filters was 30 meters long, and initially they were out in the open, and they found that the UV light damaged the filter cloth, and so they had to build a roof later. So that was a consideration that they hadn't acknowledged up front. In this particular case, these are long belt filters, and part of that was that they were able to use the filtration process to wash the material and recover some of the metal that was still in the solution. So that possibly is a longer filter than they would normally use if they were just dewatering the tailings. Just some slides here of the facility itself. This is the material coming out of the plant to the main transfer point, and at this point there's a conveyor going off to the stockpile, and there's this main conveyor taking it out to the overland facility. There's a picture of the stockpile itself, and you'll see that this needs to be quite a substantial area. It needs to be properly allowed for and designed. But the problem with this type of stockpile is, what do you do with that material? And in this particular case, a lot of it was trucked away, and ideally you would want some kind of reload hopper system that you can reload that material directly back onto the conveyor belt and use it as part of your overland system. And all of this needs to take into account conveyor maintenance and all of those types of things. Right out at the dump itself, this is a picture of the stacker system and the tripper arrangement, and the dumping of the material from this elevated position and allowing it to flow out into the vacant land ahead without control on the front side of the dump, but there were controls on the side walls to do that. This bottom photograph is an illustration of a bypass node that was built so that when the conveyor was being advanced, you could still continue depositing into that area. It was found that these were quite tricky to operate, and some of those grasshopper spreaders that were used to maneuver the system around were quite small, and it did work, but it wasn't a particularly efficient system. These are just slides illustrating what it looks like. This material was just above the saturation point, and you can see that it would build up a mound and then it would slump and flow. And in this particular case, that was the method of deposition. In other sites you may not be allowed to do that, you may not be able to do that, and it might not be acceptable in terms of stability, and you may have to build it up in layers. So all of those types of things need to be thought about and built into the design of the stack itself. Just some other views. Again, you do need some impoundment or wing walls to make sure that the tailings does stay within the footprint of the design. What we found was that right next to the stacker we achieved a slope of 30 degrees, and then the material flowed out at 5 to 6 degrees, and over time that changed. This is a view of what that facility looked like in 2006 when the pivot system started operating, and you'll see that once it started pivoting, there was a gap that was left on the northern side of the dump, and it wasn't easy to fill because as it pivots round, it leaves a gap there. What you'll also notice is that the mine was a bit slow in keeping ahead with the containment walls on the side. So that's something that needs to be planned and built into the mine plan as well as the tailings dump plan. And then you'll notice that this material stockpiled out in front of the toe of the dump had to be trucked there, and that was coming from the upset conditions at the plant. So initially there were some issues with the filtration system. In time they found it was necessary to change this to a face advanced system, and it wasn't difficult to change that, and that became a much more efficient way of advancing, and then you didn't have to put extended conveyors along the waste rock wall. You could simply deposit along the full face and advance in a much more managed way with less frequent advances for this facility. There's an updated slide just to show what it looks like with those face advances, parallel advances taking place over time. And lastly, here's a slide that gives you an illustration of how the slope profile changed with time. Initially I showed you that steep slope and then the flatter beach slope. Over time it became flatter, and in time there was one continuous slope at between 5 or 6 degrees. Now that was specific for this type of tailings, and it may be very different for other tailings. This particular tailings had a reasonably high clay content in it, which contributed towards this type of slope. One other consideration they had to build into the operating of this facility was that the tailings did hang up in the chutes. It was quite a sticky material, and so they ended up with what they called a banana chute, and that banana was lined with a ceramic material to improve the flow properties at the transfer point. This slide is an illustration of what you need to do or need to think about when advancing the conveyor equipment from the back here to the crest. In this particular case it was a substantial advance that they were doing, and they had to prepare this whole platform area in front. They had to compact it to make sure that when they advanced the equipment onto that compacted surface, it had the right bearing capacity, and that the stacker would not settle or have differential settlements such that it was in a tilted position which affected its stability. So part of the preparation of this platform was to include dynamic cone penetration testing. It's a small probe that's hammered into the tailings just to give an indication of whether the platform has the right level of bearing capacity. For example, what we found is that if the dozer was able to safely work on the material, it provided a bearing capacity of 100 kPa, and we were able to confirm that with the DCP testing. So when we look at the advance of the different types of systems, whether it's a pivot or a parallel advance, we need to plan for these. Each one of them will take a different amount of time, and the frequency between them will change depending on the type of system. It is possible to advance the conveyor system in a few days. Once you've got the preparation in place, that advancement by using a bulldozer which snakes the conveyor system on a sleeper sort of basis forward, that can take a few days. So I'd like to conclude then with what the advantages are of building dry stack facilities. Obviously, you can achieve much more stable facilities if you have got a filtered material, if you are building with a cake. You don't end up with a phreatic level unless there's an excess moisture in the cake. And that may depend on the type of equipment you're using. If there is a phreatic level, then you may have to do stability analyses. Water consumption is a very big advantage. As I said, it could be reduced of the order of threefold, and coming with that are the environmental benefits. And so it then becomes an equation of the costs of dewatering versus the savings of water, and do they offset each other? And if you simply haven't got enough water, well then you have to probably consider the filtration regardless of the costs. And yes, those costs are going to be higher than the conventional disposal systems. And lastly, the whole operability of these systems needs to be well thought through. It seems like a very simple system, building a big earth stack using tailings material, but there are other factors that need to be considered, particularly the bypass aspects and what happens when the plant stops or what happens when you're advancing. So I'd like to end with that and say thank you for listening and appreciate your time.